Alright, now that we have covered the basic ideas of modern atomic theory, we are now going to get into the more advanced concepts that you are needing for AP and HL chemistry. Also, all the SL students will also be required to know this material as well. Alright, so let's just dive into our first lecture on this, which is going to be Lecture 4, Quantum Model of the Atom. Now, at this point, you should understand the Bohr model and how the Bohr model works, and electron transitions and energy shells and levels and all of that good stuff. Alright? Now, if you remember from our discussion on the Bohr model, Bohr specifically said that electrons can be only found at specific distances from the nucleus, and that he could calculate those distances and the energies that the electrons would have at those distances from the nucleus. But what Bohr did not understand is why that was. He did not understand why electrons could not be in certain places. Remember, electrons can never be between energy shells. And the first energy shell is the lowest amount of energy that an electron could have, so it would never lose energy and crash into the nucleus. Alright? So that's kind of where we're at, so think about those principles, review those principles before we go on to this more advanced stuff. Alright, so the essential questions that need to be answered for this lecture are essentially going to be: what is Heisenberg's uncertainty principle? How do electrons behave according to the quantum model of the atom? And what are atomic orbitals? You need to be able to answer these questions by the time we're done with this lecture and for the quiz that you'll be taking on this lecture in class. Alright, so let's get started. First of all, we're going to introduce to you Louis de Broglie. Louis de Broglie was a French scientist who was very much into looking at this new idea of quantum mechanics, quantum theory based on atom, and more or less looking at subatomic particles and their behavior and so forth. Well, de Broglie's going to come out with a theory based on Einstein's understanding that light has a particle wave duality. Remember that light is made up of photons, particles, that also have a wave-like nature to it. Well, de Broglie is going to go beyond just light, and he's going to express that all matter in the universe consists of particles, but also have a wave-like nature. And so everything, including baseballs or desks or even you, have not only a particle nature, but also a wave-like nature. And what he will further explain is that the larger the particle, the more particle nature that object will be like, and the less wave-like it will be. But as you look at small particles, such as electrons or protons or neutrons, these extremely tiny particles, they are going to behave like particles, but they're going to also have quite a bit of a wave-like nature to them. And so de Broglie is going to explain that electrons behave like waves. They're not just particles, but they are also waves. And with this understanding that electrons behave like waves, we now understand that when electrons are in the atom and they move around the nucleus, they do so as standing waves. Just like light, when it moves through space or propagates through space, it moves as a standing wave. So does electrons. Now, what this means then is that if an electron behaves like a wave in the atom, there are going to be certain places that the atom, certain places in the atom that the electron cannot be. And that is due to what is called constructive interference, where the waves cancel out. Now, we're not going to go into a lot of detail on that, but let's just say that de Broglie is going to give us a truer understanding of why then electrons cannot be in between energy shells. And that is because they have wave-like properties, and at certain locations those waves will cancel out and electrons cannot exist there. All right. So, by the way, on this PowerPoint, make sure you write down everything in red. These are important points that you need to have in your notes, as well as anything else that we talk about here that's important that I stress. All right. All right. So that's de Broglie. Now, Heisenberg. What is the Heisenberg uncertainty principle? Now, because of our understanding now that electrons have wave-like properties in the atom, and they move as waves, standing waves within the atom, this brings up a new understanding that's very important called the uncertainty principle, or Heisenberg's uncertainty principle. And that is, because an electron travels as a wave, we cannot know where an electron will be at any given moment. And you can see this from this first point here. We cannot know where an electron is at any moment in time and know its momentum. All right. Now for this class, instead of worrying about the momentum of electron, the momentum electron equates to the energy that electron has. So in simple terms here, we cannot know the exact location where an electron will be at any given time if we know the exact amount of energy that electron has. Now that is really important, all right? We'll look at that some more in a minute. So what we can say or hope for is the best we can hope for is to have a probable location. Now, this word probable is important, so I'm going to underline that. A probable location. So we can know the probable location of electron at any given moment, knowing the electron's energy. So Heisenberg is going to say, well, if you know the energy that the electrons have, then you can only know its probable location, where it might be. Or if you know the location of the electrons, then there's no way of knowing exactly the energy that the electron has. And so for us, in our modern structure of the atom, it's more important for us to know the energy that the electron has and just knowing the probable location of where it will occur. And again, the reason why we can only know the probable location is due to the fact that the electron has a wave-like nature. All right, so there's Heisenberg's uncertainty principle. All right, so what are the fundamentals of electrons and atoms? Now, all of these are in your notes, and I'm going to run through them just briefly, but you need to learn each one of these points and understand them very well for both the quiz and the test and for what's coming up later in this lecture. So first of all, electrons are negatively charged subatomic particles that you know. They have wave-like properties, which we've just talked about. And the reason that if light exhibits particle aspects, perhaps particles of matter show characteristics of waves. So that's de Broglie. So we know that they're negatively charged and they have wave-like properties so far. All right, second point. It is impossible to know the location and velocity of an electron at the same time. And again, that's Heisenberg's uncertainty principle. And instead of worrying again about the momentum or velocity, we're worried about the energy. So we cannot know both. We can either know the location or the energy of an electron. All right, the third point is, if the velocity of an electron is known, the energy of the electron is known by the equation E equals 1/2 mv squared. Okay, so make sure you understand that. But if we know the velocity of an electron, we can know its energy, and we talked about that with the photoelectric effect. Okay, the next point, if the velocity of an electron is known, then only the probability of where an electron can be found in an atom is determined, and that again goes along with the Heisenberg uncertainty principle. So probability, if we know the velocity of the electron, where it's going to be found in the atom. Oops, that's terrible underlying. Be determined. All right. All right, so now that we kind of understand the nature of electrons, now we can start getting into the actual quantum model of the atom, the fundamentals, what we believe the current atom or current model of the atom looks like. And all of this is based upon mathematics. And the mathematics is pretty advanced, so instead of worrying about all the mathematical equations, we're only going to talk about the solutions to those equations and how it builds our new model, our current model of the atom. And really, this is the cutting edge ideas in quantum physics and chemistry at this point. All right. So first of all, understanding the nature of electrons now leads us to some of these points here. Electrons cannot exist just anywhere with respect to the nucleus. They can only be found at certain discrete specific distances from the nucleus. That comes from Bohr. And so we still continue to have that idea in our current model, all right? That electrons can only be found at specific places within the nucleus, all right? The problem is that we can only know the probability of those places, which you're going to learn in just a minute, all right? Next, these distances correspond to energies. That is important, and we talked about that with the Bohr model, is that at different distances from the nucleus, you have different energies. And as you move further away from the nucleus, the electron gains more energy. All right, and you should know that from the Bohr model, as we've talked about. All right, now we're going to get into some of the new stuff, new aspects, and that is using Schrodinger's equations. Now, Schrodinger is going to develop the mathematical equations needed to really give us an idea of the probable location where we can find an electron in an atom. Remember, we can never know its exact location. We cannot do that. If we try to find the exact location of an electron and know its energy, just by the act alone of trying to find the location of the electron, we alter its location. So we just never know. So all we can say for a certain degree is where most likely that electron will occur. And that's what Schrodinger's equation is going to tell us, or equations is going to tell us where most likely we're going to find an electron within a certain region of space within the molecular atom. So I'm going to highlight this whole thing. This is so important, understanding this point here. All right. So therefore, the wave function are the solutions to Schrodinger's equations. And so what we're going to do is look at these solutions that are called wave functions. Another particular word for a wave function is atomic orbitals. And atomic orbitals have quantum amounts of energy. And in reality, quantum orbitals or atomic orbitals are simply probable regions or probability places where an electron will occur with a certain amount of quantumized energy or fixed energy, right? So let's kind of diagram this. According to Schrodinger, what he did is with his equations is he was able to map out probable points where an electron would occur. So I'm going to do this right now. I'm going to put a whole bunch of points. Where an electron could possibly occur. And what you're seeing is an actual solution to Schrodinger's equation here, like so. Alright, now what does each dot represent? A probable location where an electron occurs. So you might want to write that down. So each dot indicates where an electron might occur. Now where the dots are heaviest at, and that is in towards here, this is where they're most likely to be found. Okay, so the heavier, the more dots there are, the more probable that an electron will be found. All right, now this creates a geometrical shape. It looks kind of three-dimensional spherical. Okay, so we kind of call this an electron cloud. Might want to write that down. Or an electron orbital, atomic orbital. Atomic oops, hold on. Oh, got erased. Shoot. Alright, so let me kind of just circle that again. So, well, if you look at this next slide, you can see some ideas of atomic orbitals here. You got, here's that kind of the diagram I was showing you, where you have all of these high probability points that are in the center here, creating this atomic orbital, and most of the electrons are going to be found within that region of space. And where there's only a few dots, that's just where we could probably find an electron, but it's not as probable. All right, and so this creates this three-dimensional orbital, looks like this, and this is known, we call this an S orbital. And any time you see spherical orbitals, they are S orbitals. So again, anytime you see a three-dimensional spherical orbital, it is considered an S orbital. All right. Now there are other types of orbitals that exist out there. There are what are known as p orbitals. Now these p orbitals look like they're dumbbell-shaped orbitals. So when we kind of draw, you can see that there's this lobe here.
The following student.
Alright, so sorry about the interruption there. So let's look at the shapes of these p orbitals here. So as I was drawing here, you got these p orbitals kind of look like dumbbells. They kind of come like this. Actually, let me make that a little bit better, dumbbell shape. Not so thick. Okay, so goes around like so. And another one here. There. Now, electrons can exist anywhere in here and anywhere in here. So somewhere in here, in this p orbital, oops, or somewhere in the p orbital, there's an electron that occurs there. All right, and the more densely packed it is, so specifically in the center area, where there's more dots, there is a higher probability that an electron is there. Same thing with over on this side of the dumbbell. In here, this is more likely in the center where an electron will exist, has a higher probability. But no electron can exist in between this area. So this area, no electron. There's no real probability that an electron will occur. So if I redraw that, you can see these dumbbells down here, and there are three different types of p orbitals. There's a 2px, there's a 2py, and a 2pz. Or sorry, there's a px, a py, and a pz. All right, and we'll talk about what the 2 means a little bit later. And so we can. The only difference between these three p orbitals is their spatial arrangement. The py is along the y-axis, the pz is along the z-axis in space, and the px is along the x-axis in space. So if we go back, let's see, go back to here, I'm going to write this down. So if you think about, oops, if you think about this, if I have an axis x, so this is my x, this is my y, I can have a p orbital along that axis and one along this axis, and then one along this axis and one along this axis. Alright, so this is the py and this is the px, and so the pz is actually going to come out of the plane here. And so the best way we can draw that is kind of go here and here, and this is going to be the pz. Alright, so there are three different types of p orbitals, py, px, and pz, and all of the differences is the spatial arrangement. Alright, so let me erase this. And again, all these orbitals are showing us is a solution to Schrodinger's equations, giving us the probable location where an electron could occur. And so right now we've learned that we have s orbitals, which are spherical, looks like this, and then we have p orbitals that look like dumbbells, sort of like that. And then, so there are three of them, three different types. So this is a py, this is a px, and then we have a pz that kind of goes out. Alright, and so anywhere in here, you're going to have probability points where electrons can and do exist. But we can never know 100% exactly which point that electron will be at. Alright? Alright, now, besides p and s orbitals, there are also some d orbitals. And this is what d orbitals look like. There are 5 of them. And so you need to know 5. There are 5 d orbitals. And the only difference between these 5d orbitals is mainly their spatial orientation. So this is 1, 2, 3, 4, and 5. And this diagram here is all 5 of them combined together, what it would look like. Most of them the same. The only weird one is this one here. It is kind of has a donut hole with 2 lobes or dumbbell shapes that go through there. Alright, so these d orbitals are kind of strange. Now, you do not need to know how to draw the d orbitals, but you do need to be able to draw an s, and you need to draw the p orbitals. So bottom line is, you need to know that there's one type of s orbital, there are 3 different types of p orbitals, and there are 5 different types of d orbitals. Alright? Now there are also f orbitals, and there are 7 f orbitals, and I'm not going to show you a diagram of them, and you're not going to be required to really work with the f orbitals that much, but there are 7 of them, and they're really strange in their geometrical shape or solution. And the other thing I want you to really make note of this, as we go back and we look at this drawing here, is that these orbitals, they are only mathematical solutions to equations where they show probability where an electron will occur. They're not really out there. As far as you can't pierce into an atom and see these probability points. It doesn't occur. And so, needless to say, the probability points that create these orbitals more or less create what are called electron clouds. And within an electron cloud, and you can see from here, this is an electron cloud, so an electron can occur or be anywhere within this region. And there's thousands upon thousands of probability points within a cloud. And you can see all of these clouds. Well, these clouds are in conjunction with Bohr's energy levels. So Bohr is correct in saying that electrons can be found only at specific distances from the nucleus. However, we have to modify that a little bit because more or less that electrons can be found at specific distances within an electron cloud, or a probability where an electron would occur within that cloud region. Okay, so I hope this makes sense to you. I know it's pretty advanced, so basically I would suggest that maybe you re-look at this video as well as get into your textbook and that talks more about the quantum model of the atom and these electron clouds, is specifically these orbitals. And the orbitals are what's important. So make sure you re-look at this and study, take good notes, so forth. Alright, so last little bit here. There are 7 different types of atomic orbitals: S, P, D, F, G, and H, and I. Alright, orbitals. And sometimes these orbitals are referred to as subshells. Okay, so here are the different types of orbitals, also called subshells. The ones that are really the most important are the S, P, D, and F for you, and specifically, as I mentioned earlier, the S, P, and D. Alright. Now, while in a given shell, all the orbitals are at roughly the same distance from the nucleus, as we said, there are roughly, and therefore roughly the same amount of energy. The S subshells are lowest in energy, then followed in order by the P, D, F, G, H, and I. In other words, within a shell, not all the subshells are at exactly the same distance from the nucleus. Okay, and so that's what we're going to look at here. So when we re-summarize this, so as far as energy is concerned, S is the lowest in energy. Okay, then P, then D, and then F. And those are the important ones. So energy, in these subshells gets larger or increases as you move in this direction. Alright, so now in our next lecture video we're going to talk more about where these subshells are, or these orbitals within energy levels, and spend a little bit more time with this. Okay, so that's it. I believe, yep, that's it for this particular lecture video. And so again, go back and relook at it if you need to, and I'm sorry about the interruptions that occurred. Alright, that's all for now.